Every time you connect a device to a network, something quietly hands it an address. And at scale, that something becomes a serious engineering problem. Welcome to Lesson 35 of the Dargslan Networking Mastery Curriculum. In this session, we're going beyond the basics of DHCP into its advanced features, and then into IPAM, the discipline of managing IP space when you're dealing with thousands or even millions of devices. So here's the roadmap for the next few minutes. We'll start with DORA. That's discover, offer, request, acknowledge, the four-step handshake every device performs to get an IP lease. From there, we'll cross subnet boundaries using DHCP relay, then dig into the real production knobs, scopes, reservations, and options. And finally, we'll zoom out to IPAM, IP address management, where you stop thinking about single leases and start managing address space as a whole. Before we dive into DORA, let's anchor the fundamentals. DHCP was standardized back in 1997 as RFC 2131, runs over UDP, port 67 on the server, 68 on the client, and it's stateful, meaning the server keeps a ledger of every lease it hands out, typically for 1 to 7 days, and it doesn't just give you an IP, it delivers the whole starter pack, subnet mask, default gateway, DNS, even NTP. Picture an office of 200 employees without it, 200 manual configurations, IP conflicts everywhere, a help desk ticket for every new laptop. DHCP turns all of that into plug in, get online. So how does that magic actually happen? It's a four-step conversation called DORA. Discover, offer, request, acknowledge. First, the client shouts into the void with a DHCP discover, broadcast to 255.255.255.5 because it has no IP yet. Any listening server responds with an offer, proposing an address and lease terms. The client then formally requests that offer. Still broadcast, so other servers know they weren't chosen. And finally, the server seals the deal with an acknowledge, delivering the IP, mask, gateway, DNS, and the lease countdown. 4 packets, and you're on the network. But here's a problem. This aside, that discover broadcast only travels within its own subnet because routers, by design, don't forward broadcasts. So what happens when your DHCP server lives on a different network? That's where the relay agent steps in. You configure IP helper address on the router's interface, pointing at the DHCP server. When a client broadcasts, the router catches it, converts it into a unicast packet, and forwards it across to the server. It also stamps in the JED, the gateway IP, so the server knows which subnet scope to pull from. Replies come back unicast to the relay, which rebroadcasts them locally to the client, one router, bridging 2 worlds. Now that we've got packets reaching the server, let's look at how that server is actually configured. And it rests on 3 pillars. First, scopes, the pool of addresses available per subnet, like 1010, 10100 through 200, with infrastructure IPs like your gateway carved out. Second, reservations, pinning a specific MAC address to always receive the same IP, perfect for printers or servers that need predictability. And third, options, the extras bundled with every lease, like option 3 for the gateway, 6 for DNS, 15 for the domain name. Scopes give the address, reservations guarantee it, options furnish it. Let's zoom in on those options because they're standardized by RFC 2132, and each one has a number you'll see again and again in configs and packet captures. Options 1, 3, and 6 are the Holy Trinity, mask, gateway, DNS, without which the client basically can't function. Then you've got 15 for the search domain, 42 pointing at NTP times servers, and 51 setting the lease duration. Further down, Option 66 hands out a TFTP boot server for things like PXE provisioning or IP phones pulling firmware, and Option 82 is the relay agent's fingerprint, telling the server exactly which switch port the request came from. Invaluable for security and tracking. And Option 150, that's Cisco's proprietary twist on TFTP for their phones. Now let's put theory into practice on a Cisco router, perfect for small offices or branch sites where the router itself plays DHCP server. First, we carve out addresses we don't want handed out, the gateway, static servers, the top of the range for network gear. Then we define a pool for VLAN 10, set the network and mask, plug in the gateway as option 3, DNS as option 6, the domain name as option 15, and a 7-day lease. Finally, step 3 reserves a fixed address for the Office printer by matching its MAC. Notice that O1 prefix in the client identifier, which signals an Ethernet hardware type. One quick show IP DHCP binding, and you can see every active lease. So you've got your lease, but it's not forever. Picture an 8-day lease as a timeline. At the halfway mark, day 4, the client quietly tries to renew with a unicast DHCP request, straight to the original server, and a quick DHCPAC resets the clock. If that server's down, we hit T2 at roughly 87.5%, day 7, and the client broadcasts, asking any DHCP server to rescue the lease. If nobody answers by day 8, the IP is gone, and the client falls all the way back to DHCP Discover, possibly self-assigning an IPA address in the 169.254 range while it waits. Now scale that lease management up. Imagine 100 sites, 50 subnets each, both IPv4 and IPv6. You're suddenly tracking over 10,000 subnets, and a shared spreadsheet just collapses under conflicts, lost allocations, and zero audit trail. That's where IPAM, IP Address Management, takes over. One central database for every subnet and address, with conflict detection baked into the design, tight DNS and DHCP integration, so allocating an IP auto-creates the records, plus APIs that let Terraform or Ansible grab free IPs on demand. Throw in audit logs and usage analytics, and tools like InfoBlocks, IPAM, or Netbox become the system of record for your entire address space. With all that theory in place, let's talk about what actually breaks in the real world. If your DHCP server lives on a different subnet than the client, broadcasts die at the router. You need an IP helper address to forward them. Forget to exclude your gateway from the scope, and the server will happily lease out 10.1 to some random laptop, taking the network down with it. Rogue DHCP servers, usually somebody's home router plugged into the wrong port, get shut down with DHCP snooping. Pool exhaustion bites during all-hands meetings, and when you see a 169.4 address, that's a PIPA telling you the client gave up waiting and the relay or server is down. So let's tie it all together. Remember 5 things. DORA is the 4-step handshake riding on UDP ports 67 and 68, starting as a broadcast and settling into unicast. When clients and servers are separated, a DHCP relay carries the conversation across subnets. Scopes, reservations, and options are the knobs you turn to shape what each client receives. Leases renew at the halfway mark. Try harder at 87.5% and fall back to IPA if everything fails. And finally, IPAM is what graduates you from spreadsheets to real, audited, integrated IP management at scale. And to make all of that stick, here's your cheat sheet. A single page you can screenshot and keep nearby. DHCP, defined by RFC 2131, runs over UDP ports 67 and 68, with DORA as its 4-step heartbeat: discover, offer, request, acknowledge. Add the relay agent for cross-subnet reach, scopes to define your lease pool, and reservations when a device needs the same address every single time. That's DHCP in one glance. And that wraps up our deep dive into DHCP. Next up in Lesson 36, we shift gears to NAT and PAT, the clever translation magic that lets all those private IPs we've been handing out actually reach the public internet. If you've enjoyed this lesson, head over to dargslan.com or the YouTube channel for the full series. I'll see you in the next one.